So what we're going to do with the other 4 or 5 minutes class, we have 2 other sections to teach before the end of the week. So let's get started. So I'm going to leave this up as I hunt down where the next set of notes are. 2.6. Oh, man. All right. Nope, not what I wanted. Where's what I want? Oh, here's the next set of answers. Perfect. Now we just need the next set of notes. All right. Someone's house is on fire. Got 45 minutes. See how far do you think I can make it all the way through? I assure you I could teach all these notes in like 20 minutes, but none of it. The understanding level might not be there. Let's just get to 5. If we get to 5, I'll be happy, right? All right. I love my calculus classes. Like, are you going to teach this fast every time? I was like, yeah, because you have 2 options, right? I can either not teach you parts of the book and still test you on it, or I can just teach slightly fast and then you can watch. You can just watch the lectures on YouTube and slow it down then. And I was like, let's do the latter. Okay, I had a feeling. Have you guys ever been in math class? Well, I expect you to know everything out of the book, and so lectures will not be all inclusive. I'm like, yeah, that's not good for a math class. You guys had that before? All of a sudden you get to a test like, where did this come from? Had it in physics. Oh, dude, physics was the worst. There's stuff I remember doing stuff in physics like we didn't need anything close about what this looked like. Oh man, it was a rough. I took physics here at UNLV. I guess I'll tell the story because this will get cut out and you won't hear it on the videos. I took it here at UNLV, and all my classes I took were, they're all graded on a curve, which is like, oh, that's great, right? No, one of the teachers, who is unfortunately no longer with us, really nice guy, but kind of a strange, says, I don't believe in inflation of grades. C should mean average. And so he took his grades, drew the middle line, and he failed half his students. To take his class twice. It's just like, well, I had to be in that class and fail. Great. Oh man. Anyways, and then I was in this modern physics class where they teach you quantum mechanics and all this other stuff, and you know, it seems like, oh, I found this really cool way of doing homework. It's like, you can't do it that way. Then it took me 5 seconds to dawn on it. If everything's graded on a curve, they were purposely sabotaging other people's grades. Oh man, this is terrible. Oh man, I still have one of my friends in there. He was hilarious. He ended up working on rocketry, right? And he's I don't remember where he went. He doesn't work for SpaceX, but he went somewhere, and I kept in contact for a while. I mean, he got married, and he used to do stuff that would just drive his wife insane. He's like, why didn't you empty the dishwasher? And he go, it doesn't take a rocket scientist to empty a dishwasher. I'm like, dude, keep that up. You're not going to be married long. Anyways, let's talk about math now. We got it already. Oh. Anyways, so let's talk about systems of equation and Gaussian elimination. So your quiz this week will be how to solve one of these by hand. So let's go through it. I'm going to teach you how to do this by hand. I'm going to teach you how to do this in calculator for any size of system of equations. You guys will probably exclusively only use the calculator from now on, but we'll do it by hand for a second. So let's talk about what does it mean to be a system of equations. So a system of equations has this little bracket right here. That means these 2 equations occur simultaneously, right? And that means both of these And a solution must satisfy all equations. And what I mean by satisfy, makes them true. So is this a solution? So just to test if something is a solution, we're going to just type in everywhere I see an x, I'm going to put in -2. And when I plug in variables into an equation, I always put it in parentheses to make sure that I respect the negative correctly, and that like if I square the negative, because there's this, -4 squared is not equal to minus the quantity of -4 squared. Minus the squared this is not equal. And so that's why I always plug it in. So you always respect the substitution. All right. So if I plug through this, I indeed get -3. So this one's correct. But not only does this one have to be correct, this one has to be correct. So I have -2 times -2, which is +4. And then I have 2. Oops, that doesn't go in that. 2 times the 3. And that gives me 10. And so here, in order to be a solution, it must satisfy. These look like checking marks. So this one works and this one works. Okay, so here, that's what it means to be a solution. It satisfies all of them. So you probably learned a couple different methods, maybe. I come to find out sometimes you guys don't know how to solve any system of equations, and I cry a little on the inside. But we'll get through it. So one of the common, what you mostly tend to do for nonlinears, this is what you have to do. Elimination doesn't work that well. I mean, it can. It's substitution. You solve one equation for one of the variables. You take what you got and you stuff it back in. So you substitute back into the other equation to get a value. And then once you get a value for that one, you go back to the first one, get back the other value, called back substitution. So that's what you've done before. The other way you've done it is you've added some multiple of one to another to eliminate one of the variables, added them up, and then you have an equation, one variable, figure out what that is, and then go back. So those are the two things you probably have done. So let's do them, right? So you can remember how to do them. And then we'll look at some different other ways of solving this. And then we'll get into the numerical way, which is the more important way. All right, so here, if I was going to solve this one, I will do, let's do elimination on this one and substitution on this one, because elimination on this one doesn't work too well, but it works well. So here, notice here I have this one, I have a -y and a +2y. So I'm going to multiply this whole equation by 2. So I'm going to take this, so this will be 3x plus 2y equals 14. And then I'm going to take, so equation 1 and then equation 2. So this is equation 1, I'm going to put 2 times equation 2. So 2 times equation 2 is going to equal 2x minus 2y equals 4. And then what you do is when at this point you add them up. Have you guys seen this before? Or you've done this before? See most people nodding their head yes. Okay. If not, I may slow down a little bit just not to lose. But if most people have seen it before, we'll just go ahead and go ahead. So here I'll get 5x. Here I'll get 0 by design. So 5x is equal to 18. So what is x equal? Well, x equals this awful number, 18/5. Well, yay, right? Then I can just plug this back into 2. So I'm going to go back to equation 2. I know what this is. This is 18/5. I'm going to minus out a y, and I'm going to get 2. If I solve for that, you guys seen this symbol before? This one, where the equals plus the arrow means implies. It means, instead of writing, it means this implies that y is equal to 8/5. It's just a nice way of saying, instead of writing it on the next row, because usually when you do math, you'll like do a line, do a line, do a line. If you do a line and you don't want to write it on the next line, just write implies the next line. That's what it means. What you're secretly doing here is you're always saying this implies this, which implies this, which implies this, and that's how you're doing your math. But if you do it on the same line, you tend to write the imply. All these tend to be assumed when you don't. When you're doing formal math proofs, you'll do this implies this implies this. That's how you write them. Now, even in then, you don't always write the explicit implies. I'm on the wrong layer. That's good to know. So here we have our solution. Our solution to this, hold on, let me write out my solution very clearly. It's 18/5, 8/5. Did I do that right? Yeah. And so here's here's our solution. Remember, our solution is an ordered pair. It's two things. You can write out, or you can box both of this. If you box this, that'd be also okay, because then you have what x is and what y equals. All right, so the other method is substitution. So I'm going to take equation 1 here. I'm going to solve it for y. So y equals 1 minus 2x. I'm going to plug that into equation 2. So this is going to be 3x plus 4. I know what y is. It's 1 minus 2x equals to 14. Now that I know that, I can simplify. So this will be x plus 4 minus 8x equals 14. So I have minus 5x is equal to 10. That means that implies x is equal to minus 2. And then once I can just plug that back into 1. So 1 is 1 minus a minus, or oops, hold on, minus 2 times a minus 2. So that gives me 3. No, that gives me 5. I can do math. 1 minus 4, or 1 minus a negative 4, would be positive 4, gives you 5. And so my solution here is minus 2 and 5. Okay. So this was elimination, and this was substitution. So you've probably done it for a 2x2 system. Have you guys done it for a 3x3 system? Yes, some people yes, some people no. Some people don't remember. All right, so let's do it for. All right, so if we're going to do this graphically, we're going to graph all the lines, right? And then it's just the intersection. So here for the 2x2 systems, we can have exactly one solution, no solution, infinite solution. This is actually just easiest seen graphically. So here, if I have my first equation, so if I equation 1 and then equation 2, this will be my answer. Just wherever the intersection is, this is my answer. But you can also have it where the lines do not intersect, right? So here's to make this equation 1. This will be my equation 2. And since they are parallel, just assume that these are parallel, right? These will never intersect, so there's no solution. Or if I have equation 1, and then here in red, it's also equation 2. We have infinitely many solutions. And an example of this would be if I had y minus, or if I had x minus y equal to 0, then 2x minus 2y equal to 0. If this is my system, all I need is x equal to y. Anything that's on the x equal y line works, right? And so this has an infinite number of solutions. All right, so let's get into a 3x3 system. Let's get into a 3x3 because once if you can do a 2x2, you're doing good. If you can do a 3x3, if you can really know how to do a 3x3, you can really do an n by n, right? And infinite. I could give you any finite amount of values, variables with that exact finite amount of equations, and you should be able to produce a solution. So on the exam, we're going to do 10 by 10 and watch your brains ooze out. Actually, if you're allowed to use a calculator, who cares, right? You just type it into the big beast and be done with it. Let's go through this. If I wanted to solve this, what would I do? What would I do to solve this? Do you know what at least one of the variables is? Sure, right?
Just
you know
plug.
Yeah. Go for it. Go for it. Someone almost said it.
Yeah, just plug z into it. You'll get y equals -1. And you could plug everything into the top equation.
Yeah, that's it.
Find out that x equals 0.
Perfect. And so here, when we do this, that'll be exactly it. So here we plug this in. So we have z equals to 3. So I know what the first part of my solution is, right? It's 3. So here, I'm going to plug 3 into here. So I plug 3 into here. So I have y plus 2 times 3 is equal to 5. That means y equals -2. Oops, no, -1. I can do math. This is V6, move it over, -1. So we have -1. So now I have that. So I have x minus 2 times a -1 minus 3 equals 1. So here I'll have +2, -3, and I want x equal to 1. So x in this case was 2. And then we get our solution. Okay, so once we get, so if I give you anything in this form, you just back substitute, get a solution, then you have 2 solutions. You're going to back substitute in this one, get that solution. So given anything, we're going to try to get it into this form. And so here are some operations we can do that give equivalent system. These operations do not change the solution of the system. And I'm going to explain this since we have time exactly why. If I wrote, I'm going to write notes here that which I will erase later. So I'm going to write explaining notes here, but I only need, let's see if I can help you guys when you type notes. I only need this much space to solve the problem. I know that already because I've done it before. So here, let's just look at, let's look at this one. If I'm going to interchange one equation for another. So if I took this and I call this equation 1, this equation 2, and this equation 3, if I wrote this system here as x plus 2y minus z equals 13, x minus 2y plus 3z equals 1, 3x plus 2y minus 5z equal 3. If I changed the answer to this in any way, the answer is no, right? Because if x, y, and z worked for equation 2 before, it's going to work for equation the now equation 1, right? It's the same equation, right? So interchanging will have no effect on the solution. I'm just moving stuff around. I could easily call this equation alpha, this one equation moose, and equation Captain America, right? For who I care, right? It doesn't matter what I name them or how I label them, how I deal with them, right? I could do whatever I want. And so interchanging one equation for another doesn't matter. If I multiply one equation by a non-zero constant, that's fine, right? If I take this whole thing again, and here, let's just say if we take this, and I'm going to have x plus 2y minus z equals 13. And then I'm going to say this is 2x minus 4y minus 6z equals 2. And I take 3x plus 2y minus 5z is equal to 3. So all I've done is taken this equation and multiplied by 2. Have I changed any of my solutions before? No. This should have zero effect on the solutions, right? Because here, if the correct answer x, y, and z satisfy this equation, it will also satisfy this equation. The only one that's kind of weird is I can add a non-multiple zero from one equation to another. And see if I can explain this one see if I can explain this one. So I'm going to take equation 1. I'm going to take x minus 2y plus 3z. So I'm taking the equation 1 from this side, and that's equal to 1. And then I'm going to add 13 to both sides. Can I do that? Can I add 13 to both sides?
Why not?
Sure, why not, right? But what do I know what 13 is? Is 13 also equal to this? Yeah, that's what that equation says. That's 13. And so instead of writing 13 here, I'm going to write x plus 2y minus z. So if I add this to this side and add this to this side, have I changed the equation at all? No. So what would have solved this will also still solve the new one. And so this is the only one that's kind of weird. So I can add multiples. So if I added, instead of 13, I put in, oops, of course I was on the wrong layer. I'll just go back. I could have added 26. And I can add 26 to both sides. Well, in this case, I have to add 2x plus 4y minus 2z, right? Because that's 2 times this, right? To both sides, and I still get the same thing. So this is the one that's a little harder to understand why it works, but it's perfectly fine. All right, so now we've done all this, but what have I done here? I made what they call upper division math alphabet soup. You just move stuff around. You haven't done anything useful, right? So let's do useful things, right? Let's do useful things. So here, if I label all this, my useful thing is I'm going to take this. I want to get rid of this right here, right? And I want to get rid of this right here. And so what am I going to do? I'm going to take equation. So I'm going to rewrite this equation. And I have x minus 2y plus 3z equals to 1. And then I'm going to take, instead of equation 2, I'm going to take equation 2 and I'm going to add to it a negative 1 times equation 1. Now, can I do that? Sure, right? I'm allowed to add a non-multiple 0 of one equation to another because of this logic, right? If I add 26 to one side, I can add 26 to the other side. And so since these are truly equal, if I add a negative of this to one side, I can add a negative of this to the other side. But why would I do such things? Well, obviously, if I add negative of this to this, I'm going to get 0x, right? And so I just have nothing here. Negative of 2y added to 2y would be 4y. Negative of 3z added to negative z would be minus 4z. And a negative 1 added to this will give me 12. Okay, so I've done that. I can do that. And in fact, I can do this again. I can take equation 3 and I can add to it minus 3 times equation 1, right? So I'm going to take this equation and add negative 3 of the first one. So negative 3 to this will give me 0 again. Minus 3 here would give me 8. So 2 minus a negative 6 will give me 8. And then negative 5 minus 15. Yes. Hold on. Minus 20. Am I doing this right? All of a sudden, my notes are not complete, and I'm worried about it. Hold on. I'm pretty sure I have the answer in 2 seconds. No, I never finished this one. No, I'm just full of crazy. Yada, yada, yada. All right. And that would equal 3 minus 3 of negative 1 would be 0, right? Does everyone see what I did here?
I think it should be negative 14z for that last equation.
You're probably right. 3 times, oh, yeah, because I can't do math. Thank you. So this is minus 5 minus 9 would be minus 14. Equals to 0. Yes. Okay. So let's make our lives easier and let's solve this. So here I'm going to rewrite the same first equation. This equation, I'm going to divide it by 4. So here I'm going to take equation 2 and I'm going to multiply it by a 4th. Now, why would I do such a crazy thing? Well, if I divide out 4, I'll have y minus z equals 3. And then 8y minus 14z equals 0. All right, now I'm going to take this equation. I'm going to leave it the same. And then I'm going to take this one and I'm going to minus, so I'm going to take equation 3 and minus out 8 of equation 2. Now, why would I do that? I get rid of the y. And so if I minus out 8 of equation 2, I get nothing. So I'll have nothing here, nothing here. So I'll have minus 14, hold on, minus 14z minus negative 8, so that'd be plus 8, so that'll give me, I can do math, 6z, right? And then minus 8 here, minus 8 here, so negative 8 times 3 would give me, hold on, minus 24. And so that means z is equal to minus 4. And if z is equal to minus 4, y is equal to, I can do this in my head, I swear. I don't have to, but this will be minus, so y plus 4, so move the 4 over, so y is equal to minus 1. And then if that's true, I have 2. I have minus 12, so I have positive, so I have negative 10. X equals to 11. I don't think that's right. Hold on. Let me see what I did wrong. All of a sudden, I don't think I did my mental math right. This is why you never ever do this by hand. I'm sure I have to type this in Wolfram Alpha so I can figure out what I did wrong. I want to do a system of equations. System of equations. It'll produce a little cheat sheet for you, and you just type it in. So let's go back to the original. Always type in the original. Yeah. I remember how I said at the beginning in class, always have these pre-figured out. I didn't finish this one, and I didn't have it pre-figured out. I had it started, and then just for whatever reason, because you actually never do it this way, except to learn what you're doing. You do it. You always do it once, so you say, "I'll never do that again," and then you just do it the easy way. Compute. All right. Oh no, that's not the right answer. I would not give myself something that terrible. Let's try this again. Yep, I messed up. Hold on. Oh yeah, if this is minus 4, if I move it over, this becomes 7. Hi. This is why you do not do mental math. This is 7, and if this is 7, this is indeed minus 14 plus 12. So it's being negative 2, so this becomes positive. Yes, positive 3. I have all the steps right except for that last one. That's why I butchered it. Yes.
I think it's a negative 6z equals 24.
That's what I did wrong. Thank you. All right, so do we ever do math this way? Let me ask you. The answer is no. We do it once to show you why you never do it this way. So let me just do the next page, and I think the next page is just where we make everything easy on you. Let's do actually. Yeah, the next 2 pages is correct because we'll redo this again, and except we use the shorthand notation, which I don't get lost with everything. Okay. Thank you. All right, so let's do this. All right, so let's look at this for a second. Let's look at this for a second before we go on. Do I need to write x every time? No, it's always going to be x in the first column. Do I need to write y every time? No. Do I need to write z every time? No, right? Just extra information which could get you all confused, including me, right? And so what we define here is what we call an augmented matrix. So we take this, and we just say, here, given any system, I'm going to write this as a matrix, which we can use to solve simple equations, and we can see this easier, right? So we're going to do this just so we have placeholders for all this. And so here, we're just going to write this out. So here we just take the coefficients of 1, minus 2, 3, 7. And then we'll have 2. Oops, hi. I don't know where that came from. 2, no. 4, 2, minus 1, 42. 3, 2, minus 5, and 5. The dotted line's up to you. You don't have to have it. I usually put it. Here's to show another example. Here, if I have the system, it'd be 3, minus 2, 1, 2. There's no x, so you put in a 0. 2, minus 1, 1. And then there's no x, no y. And then for z, we'll put in a 5. equals 15. Oops, no equals 15. And here you can have this line. And so we call these augmented matrices. And so basically we've taken all this information here and we've just thrown away the repetition to make it easier for us, right? So we've thrown away the repetition to our repetition. So go ahead and give these two a try real quick on your papers before I give you the answer. So write these as augmented matrices. I'll come back and give you the answers. I'm going to fill up my water real quick, and then we'll go to the next one. Come here. Come on, your show. Oh. All right. You guys get answers?
Yep.
All right. So here are the answers. So go ahead and check them against yours. So make sure, what I'd be very careful about is making sure you have the zeros in the right spots. If not, you get totally wrong things. Started filling up my water. All right. So let me explain how to do it the quote unquote easy way. It's not any easier. It's just less, there's less stuff everywhere. So it's just, you get less lost. All right. Yes, we will do. Okay, we don't need to finish this. Let's go to here. All right, let me actually show you page. Let me show you the top of page 6. We'll finish here with page 5. We'll do this once. And so here, let me zoom on in. So here, once we put everything into an augmented matrix, row operation. So these operations do not change the solution system. They're actually the same before. If I switch 2 rows, it's the same thing as switching 2 equations. If I multiply 1 row by a non-zero constant, same thing as multiplying an equation by a non-zero constant. If I add a non-zero multiple from one row to another, it's the same thing as adding a non-multiple of one equation to another, right? We put zeros in for, so you wouldn't put zeros in for the z columns, no, because there isn't any z's. Yes, so sometimes some equations will not have zeros. So you'll have system of equations, so you might have 5 unknowns and 2 equations. You might have 10 equations and 2 unknowns. This method actually, I'll teach you, will actually sort it all out in the wash. So it's not possible. It won't show up as possible. And the other is matrix because they do have that variable. Yes. Hey, you. Hold on. Sorry. Anyways, and so we're going to do this again for this system. We're going to go through all the steps, but let me show you what the goal is. So let's first make the augmented matrix. So let's first write this as an augmented matrix. So I want to have 1, -1, 3, 1, 2, -2, 3, -1, 5. And then we'll have 4, 10, and 14. Okay. So what's the goal here? The goal is we're going to look on page 6. So here we're going to put it in reduced row echelon form or row echelon form. It's not super important. what it means is a matrix in row echelon form has the first thing in a non-zero number in a row is a 1. We call that the leading entry. The leading entry is to the right of the leading entry above it, and all zeros below. And then we have this where if it has a leading entry, make everything in that column 0. We're going to use what we call Gauss-Jordan elimination algorithm. This is what all your computers use to solve it. And so basically, given the system of the equation, what we're going to try to do, can we not highlight no more? Thank you. What we're going to try to do is we're going to try to get a 1 up here. Once we get a 1 up here, it's going to be real easy to get rid of. We just multiply whatever constant's here. We can easily multiply this by a negative of whatever's here to make a 0, and a negative whatever here to make a 0. Then we're going to try to get a 1 here. And then we'll take the same thing, put a 0 here. And then we're going to try to get a 1 here. And then we'll just back substitute. And this actually prevents this back substitution. So the boxes mean whatever. And so we're going to try to actually follow the algorithm this way. We're going to have a matrix that looks like this. Actually, we're starting here. We have a matrix that looks like this right now. So our next goal is to put zeros here. And if you deviate from this, you're going to kind of ruin your work. Because if I get a 0 here first, right, for say, I get a 0 here first, but I haven't zeroed out this row, when I zero out this row, I'll probably ruin my 0 here. Just how it works. So there's a very particular method. You always follow this, and after you do it like 2 or 3 times, you have it in your head. So let's do it. Let's do this one. And I'm going to show you kind of shorthand notation. So I'm going to show you my shorthand notation. So I'm going to take a copy of this row. I'm going to take -1 of this row and add it to this row. And how I show that is I just do a little arrow, say -1 times that. I'm going to do this one kind of slow, and then I might do the other ones a little bit faster so we make sure we get done on time. So the first row hasn't changed, so I'm going to rewrite that row. The third row hasn't changed, so I'm going to rewrite that row. And what sucks about doing these, if you make an algebraic error anywhere, you have to go all the way back, and it takes forever to figure out what you did wrong. Forever, trust me. I hate writing these because I'm like, okay, where did they go wrong? And it takes me years. Now, if I take 1 minus negative of this row would be 0. 2 minus negative of this row would be 3. So 2 minus a -1 would be +1. So 1 plus 3, or 1 plus 2 is 3. -2 minus -3 would be -2 minus 3, sorry, it gives me -5. And then here I'll have 10 minus 4, which will give me 6. Is everyone okay with the first step? Any questions how I went? I'm just taking negative of this row, adding it to this row. No? Okay, I'm going to keep moving forward so we can finish this page by the end of class. All right, so here, I'm going to just take -3 of this row and add it to this row. Why? Because that will cancel out this and make this a 0, which is our goal, is to get zeros and zeros. That's our first goal. So it'll be 1 minus 3, 0, 4, 0, 3, minus 5, 6. Often I'll do both of these at once on the same line, but for when I'm first teaching it, I shouldn't. So this is a 0 by design. So 3 minus 3 is 0. 1 plus 3 would be 2. 5 minus 9 would be -4. And then 14 minus 12 would be 2. Okay, so that's where we're at. So let's look at where we're at in our algorithm. So where are we at in our algorithm? We have achieved, so we went from a matrix, we put a 1 up top, and now we have 2 zeros here. So our next goal is to put a 1 here. That's our next goal. So I could divide this, I could divide row 2 by 3, and I'd achieve that goal, but then I'd have a fraction here. And who loves fractions? Nobody, right? But notice if I divide this row by 2, it divides nicely by 2. So what I'm going to do is I'm going to switch these 2 rows. And when my symbol for that is just an arrow here and an arrow here. And the reason I'm switching those 2 is it'll make my life easier. That's 1, -3, 4, 0, 2, minus 4, 2, 0, 3, minus 5, 6. Oops, that's a funny looking 6.
I think you missed a negative on top.
You're right. Thank you. Because if I didn't copy that out, I would have carried on.
Yeah.
Forever. Thank you. All right. So now that I've done this, I'm going to divide this row by 2, and I just draw a little division by 2. That's how I write it. So when we do that, I'm going to get the following. So I'll have 1. Oops, my computer's getting a little chunky. 1 minus 1, 3, 4. Didn't do anything to that row. Didn't do anything to the bottom row, so I'll just copy that one down as well. And this one I divided by 2, so it should be 1 minus 2, 1. All right, so if we look at our little algorithm, where are we at? So now we've achieved this. Our next goal is to put a 0 here. That's our next goal. So to do that, we're going to just take minus 3 of this one to this one. So we have 1, negative 1, 3, 4, 0. Oops. 0, 1, minus 2, 1. This 0. This is 0 by design. The next one should give us negative 5 plus 6 will give me positive 1. And then 6 minus 3 will give me 3. Okay. Let's look at our algorithm again. We're almost there. Let's look at this algorithm. So we have a 1 here. Or we actually achieved, we not only got this, but we got this as well. So the next thing we want to do is 0 out here. So we're going to 0 up. I'm going to do that in one step. And so here, in order to 0 this up, I'm going to take minus 2 here, and then I'm going to take, or no, positive 2 here, and then minus 3 here. So the first row would be 1, negative 1, and then if I'm adding negative 3 of this row to this row, it gives me 0. Negative 3 to this row will give me minus 9, so minus 5. This one gives me 1, 1. And then if I add 2 of this row to this row, it gives me a 0. And then this one to this one should give me 7. Yes. 0, up, 0, 1, 3. And then the very last thing I need to do is 0 out this one. It's the last thing in our algorithm. And so we're just going to add 1 of this row to this row. Gives us our final matrix here, which is 1, 0, 0, 2, 0, 1, 0, 7, 0, 0, 1, 3. Now, if I was going to retranslate this into what this means, that means x plus 0y plus 0z equals to 2. Here I have 0x plus y plus 0z equals to 7. And then if I have 0, 0 plus z equals to 3. And so here you can just literally read off the answer. And that is the answer, right? And you can check it real quick. Here you can check it. I do that for you right here. Here I've done it for you. So here I've checked it. And you can check each one and every one of the equations to make sure it's right. So that's what the goal is. Our goal is to eventually just do it this way. So here we have the augmented matrix. So the first thing we want is if we get a 1 here. So in order to get a 1 here, we're just going to divide this by 4. So let's do that. All right, so we'll have 1, 2, minus 1, 2, 3, 8, 5, minus 11, minus 2, 1, 12, minus 17. Okay, so now we've gone from a generic matrix to one where it has 1 here. So our next step is to get a 0 here and a 0 here. And in this one, I'm actually going to do both steps at once. So I'm going to take minus 3 of this row and add
Professor?
it. Yeah, go on.
Isn't the first row, isn't like on the right side of the line, isn't that supposed to be a 1? Where the 2 is?
Yes, you are absolutely correct. Thank you.
Yeah.
Okay, thank you. So here we're going to take minus 3 of this row to this row, just to make this 0. And then we're going to take a positive 2 times this row and add it to this row. So I'm going to do the first one, and you guys going to tell me what the answer is for the next row. You can write it in chat, or you can write just say it out loud. I do warn you, since these videos are going on YouTube, if you don't want to be, I crop them so you don't see anybody's faces, but if you don't want your voice heard, just use the chat function, okay? If you don't mind, go for it. All right, so here, so 3 minus a minus 3 gives me a 0. And 8 minus a 6 will give me 2. A 5, a minus a negative, all right, so in this case becomes positive 3, so this turns into 8. And then 11 minus 3 will give me minus 14. All right, so what do you guys get for this last row down here? Oh, someone has it in chat. Yes, that's correct. So it's 0, 5, 10, and minus 15. All right, so where are we at in our algorithm? Here, we've gone from this to this to this. So the next thing I want to do is get a 1. Well, to get a 1 here, this divides cleanly by 2. So we'll just divide this by 2. If it didn't divide cleanly by 2, this divides cleanly by 5. We just switch the rows and move it up. So let's do that. So I have 1, 2, negative 1, 1, 0, 1, 4, minus 7, 0, 5, 10, minus 15. All right. All right. So we've achieved this goal. We have a 1 here. Now the next goal is to get a 0 here. So we're just going to add negative 5 of this row to this row. So I have 1, 2, minus 1, 1, 0, 1, 4, minus 7, 0, 0 by design. Minus 4 of this would give us minus 20, or minus 5 of that would give us minus 20. So minus 20 plus 10 would give us minus 10. And then this will give me positive 35 plus the negative 15 gives me minus 20. Oh, no, positive 20. Oops. Positive 35 minus 15 gives me a positive 20. All right. Now we have this achieved. We want to get a 1 here. So we're just going to divide by minus 10. And that gives us 1, 2, minus 1, 1, 0, 1, 4, minus 7, 0, 0, 1, minus 2. All right. So we have a 1 here. Our next step is to get a 0 here and a 0 here. So we're going to just add minus 4 here, and we're going to add a positive 1 here. And so by doing that, we're going to get the following. So we get 1, 2, 0, minus 1. We're going to get 0, 1, 0, 1, 0, 0, 1, minus 2. And the very last step is we just need to add minus 2 of this up to here. And that will give us the following of 1, 0, 0, minus 3, 0, 1, 0, 1, 0, 0, 1, minus 2. All right, so once we have, oh, I forgot we were doing this last step here. That's what we're doing here. So once we have this, we can rewrite this as x equals minus 3, y, because that's literally what, if we unaugmented the matrix, y equals to 1, and z equals to minus 2, or you can write it in as a point in 3D space, and the point in 3D space is the following. Okay. All right, any questions about any of this? All right, I'm going to leave it up for a second. Quickly checking the bubbles. What do you mean? Something I'm not supposed to. But I usually take them for a walk around this time, but it just hasn't. I had to teach class. I took them for afternoon walks. Come summer, they're going to get like 6 a.m. morning walks because it's too hot outside. All right, so let's go to the next page. If you miss this, the lecture videos get posted. They'll be posted tonight or tomorrow. Tomorrow at the latest. If not, I'll just make it due later, like I did last time because I got behind trying to fix stuff. All right. So for system linear, we can have exactly one solution. We can have exactly no solution, or we can have exactly infinite many, or not exactly. There's no exact about it. You can have infinitely many solutions. You can have 1D infinite many solutions. You can have 2D infinite many solutions. It depends on what's going on. So let's talk about exactly one solution in kind of 3D space. So let's give an example of it. So if we're going to draw this in 3D space, you could just draw like 3 planes and they intersect at one point, right? Here you can have 3 planes that are parallel, or 2 of them intersect, but one, as long as one of the set are parallel, it won't work. And here, the planes can intersect at a line, or they all can be the same plane, and then it's an infinite amount of points. But let's actually look at different representations according to what will happen when you finish your algorithm. So your algorithm could look like this. You could have 0, 0, 1, 0, 1, 0, 0, 0, 1. And then you can have a star here, a star here, and a star here. And so this means any number. Hold on. Sorry. That's my brother's dog. My brother's dog is not trained at all. All right, so let's talk about no solutions. So no solutions. So right here, what is this saying? What is this saying? If we get anything that zeroes out and equals a number, what is this saying? That says 0x plus 0y plus 0z is equal to some number. Let's just say 7 for a second, right? Well, that's basically saying 0 equals 7. Is this ever true? No. So we hit, this is a contradiction. So once you hit a contradiction, we'll just say no solutions. Now, if we have infinite many solutions, what will happen is you can have something that looks like this at the end of your algorithm. And you have something that looks like this at the end of your algorithm. And now, if you have a complete 0 row, or in other words, a column here, which does not have a leading entry, so there's no leading entry here. So here, if this column Z doesn't have a leading entry, we just say it's T, and then we solve for it, okay? So let me show you at least one example of this, and then we'll do this. So here, we'll have -3, -5, +36, and 10. We'll have -1, 0, 7, and 5, and then we'll have 1, 1, -10, and -4. All right, so do me a favor. Go ahead and try to do this one on your own and get at least to the point where you have it as a non-leading number. Now, as you're doing that, I am going to open up the next set of notes so we don't have to waste time for that. So give this a try, and I will open up the next set of notes. Is that a 0? So let me, does the zeros have to be in that order? No, the zeros can be in any order, okay? Technically, a no solution can have another, let me just briefly show a couple more examples of this real quick. So another no solution could look like a 0, a 1, a 0, a 0, 0, 1, star, 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 and a 0 here. So here's another example of a no solution, right? Because I have this right here. And another example of an infinitely many solutions, I can have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, star, star. And here, since I have a 0 row, and here I have nothing here, and so here we're going to set y equal to t, right? We set y equal to t in order to say the infinite amount of these solutions, okay? All right, so keep trying this. Let me open up the next set of homework or notes. You have an answer. Does this does the no solution mean there's the whole matrix? No, it just means if it's not true, they all have to be true together or not true at all. So it's kind of like a rowing team, right? If someone dies, the boat doesn't make it. I guess that's a terrible analogy. they're all in sync with each other. So, all right. Let's open up the next set of notes. Well, all right. Let's open up Photoshop. Whoop. All right. So let's just open up the first 2 pages, because if I find if I open up like 3 or more pages, the thing just goes silly on me and stops working. Yeah, let's just do 3. I'll risk it. I'm risking it.
Could I ask a question?
Sure.
I'm not really following. How are we doing the addition and subtraction with this? Like the minus, negative.
Oh yeah. So let me do the first step really, really slowly. All right. So here, the first thing you want to do is, all right. So the first thing you want to do is get a 1 up top. How I'm going to do that is just switch rows. This doesn't divide nicely by 3. I'm sure at least one of you tried to divide that by 3 and just been working with fractions. Keep working. It's not wrong. It's just not easy. All right, so here I just switched to 2 rows. Now I choose this goal. The next thing I want to do. So here, this is your question. So here, I want to zero this out, right? So here, I'm going to be adding, in order to do that, I'm going to add 3 times this row to this row. So here, this is, so I just write that as 3. But what I'm really doing is I'm adding row 1, or 3 times row 1 to row 3, and I'm putting that into row 3. And so let me do that very slowly. So 3 times row 1 and row 3. So 3 times row 1. So here we'll have 3, 3, minus 30, and 4, right? And then here we'll add to it row 3. So it'll be minus 3, minus 5, 36, and 10. Okay, so we'll just add these up number by number. So this gives me 0 by design, right? So here we'll have, so it'll be 1, 1, minus 10, minus 4. Yeah, it's getting sluggish. I had to open.
Do you not multiply the -4 by 3 as well?
Oh, thank you. Thank you. No, I did not. Should I have? The answer is yes. So that'd be 12. All right. And so here, we just copy this over. And then here, that's when I add this up, I get a 0. When I add these 2 up, I'm going to get minus 2. So this is minus 2. If I add these 2 up, I'm going to get a positive 6. So I put a 6 here, and if I add these 2 up, I get a minus 2. I put the minus 2. Okay. So that's what I'm doing to add these rows. So that makes, does that make more sense?
Yeah, that clears things up a lot. Thank you.
Okay. All right. All right. So how many people have gotten to a solution? At least to what they think is as much as they can do. Is anyone at least there? I don't want to shortchange you. I want you to try through it once. Now, is the way I'm going to show you in 2 seconds the only way to do it? No. But it is a way to do it. So someone got, okay, so we got 1 answer. Anyone else get a different answer or a different matrix? Even if you don't know how to, even if you just list the matrix, not even without the answer. Well, at least I got 1 person to get all the way through. I'm super happy. Did you switch rows? No one first? Yes, no? Yes. Oh, okay. In step. Oh, you know what I need to show you guys how to do? I know exactly what I need to show you. I think I messed up. All right. Maybe. I got infinitely many solutions. Okay, someone got infinitely many solutions for this. So when I did it, I'm going to show you what I got. Hello. There it is. Ta! This is what I got. So I swapped these rows, added this up, these two zeroed out, and I got this. I took, this was already a 1, so we were already good to go there. Just how it worked out, this ended up being a 1. So it's already good to go there. And when I did this, I got here, and then I just cleaned it up. I just like cleaning it up to make my life easier, right? And I get to this matrix. Let me teach you how to do this in Wolfram Alpha now. Good old Wolfram Alpha. It knows all, it tells all, right? So, hold on, let me leave that up. Let me leave that up. I'm going to type in the matrix off screen so you guys can copy this down. Let me just type in the original matrix, so -3, comma, -5, comma, 36, comma, 10, close, comma, open, -1, comma, 0, comma, 7, comma, 5, close, comma, open, 1, comma, 1, comma, -10, comma, -4. Aha. All right, so let's just show you how to type this in to Wolfram Alpha. So in Wolfram Alpha, well, don't worry, I'll go back to this page. Let me just show you how to do this in Wolfram Alpha. So in Wolfram Alpha, you just type it in with each row. So you type in your first row with the little commas in between two brackets, right? And we type this in between each row with comma brackets. And here we get our augmented matrix, right? As we have here, hopefully. Is this the same? It looks that way. Now, with this many numbers in my dyslexia, am I going to get something wrong? Oh, you betcha. So what you're going to want to type in is reduced row echelon form, or RREF, right? RREF does the algorithm for you. And then presto, you get this. Ta-da! Is that our answer here? Yes. So this is just a nice way. So RREF, type in a matrix, row reduces it for you and gives it into this form. Okay? So that way you can just do that. And so that's how you're going to type in all your system of equations from now on. So let's see what we got when we got here. So once we get here, notice that there's no leading 0 here. There's no leading 0 in the z column because this is the x column, this is the y column, this is the z column, right? There's no leading 0. So I'm just going to say z equals to t. And so when I write this out, this equation literally is, hold on, there we go. This equation literally is y minus 3z equals 1. Well, that's the same thing as if I move this over, it'd be y plus 3z, but 3z is t, right? So here we are. So y equals this. And then here, minus 7z, move that over, so it'd be minus 5 plus t. So for any t, so when t is 0, I can have a solution. In this case, it'd be 0, 1, and -5, right? If t is 1, I'll have a different solution. It'd be 1, 4, and 2, right? And that also is a solution to this. And so any value of t I pick will give me a solution. Now, can I use any numbers? No. 0, 0, 0 is not a solution for this. It's just not, right? Because if I plug in 0, 0, 0, I don't get 10. So it's not everything is a solution. Infinite does not mean everything. It means anything in this. And this defines a line in 3D space, right? This is defining a line in 3D space, okay? All right. What do you mean by no leading? Oh, so no leading entry. So no leading entry. So in this column, so a leading entry is the first, let me go back to our little rules. Where are my rules? Ta-da! All right, so the first non-zero number in a row is a 1. That is the leading entry. The leading entry is the first non-zero number in a row, okay? So when we go back to here, as I wander through, the first non-zero entry we have here is the 1. So this is my leading entry in this column, right? So this column has a leading entry. If I walk this way, this one has a leading entry, right? So this column has a leading entry of a 1, right? This column does not have a leading entry. There's no leading entry for this column. And so we set that equal to t. Notice here, in our other examples I've shown, in this example, let's look at this example for a second. And I'm glad I spent extra time to talk about this example. Here, there's no leading entry in the x column. There's just not. But there is one in the y and the z column. Here, there's no leading entry in the y column, but there is for the x and the z column. So here in the x column, there's a leading entry right here. Here in the z column, there's a leading entry right here. This is the first non-zero entry in a row. But y has no such thing, right? There's no such one for y. And so therefore, in this case, we've set y equal to t, and then we'd solve for these in terms of that, okay? So yeah, you'll have more time to practice this. All right, so let's go ahead and get rid of these two, and let's do the next set of notes.